Question 16 from the 2025 Higher Physics Examination on the SQA Paper 1. A student sets up the apparatus shown to produce an interference pattern. S1 and S2 provide coherent sources of microwave radiation. A radiation detector is moved along the line from P to Q. The first minimum is detected at point X. The distance from S1 to X is 300 and the distance from S2 to X is 250 millimeters. The second minimum is detected at Y, and we asked to find the path difference between S1Y and S2Y, and we're given the following sort of responses: A, B, C, D and E. Okay, let's go to the diagram and see what we can make out. We know that looking at the first minimum, so if I go to the first minimum here and go from S1 to X and from S2 to X, I know that's going to be the first minimum. And the condition for the first minimum is the following. The path difference for the first minimum, we'll just say PD, for the first minimum is always going to be equal to half a wavelength. It's going to be equal to 1/2 of a wavelength, and I'll write it as 0.5 wavelengths. But what is the path difference? Well, we know S1 to X is going to be equal to 300 millimeters, and we know that S2 to X is going to be equal to 250 millimeters. So we can see a path difference here of 50 millimeters. So we can write that down. The path difference, if we measure it with our measuring tape, is going to be 300 millimeters. And take away the 250, and that's going to leave us with 50 millimeters. So we know the physical path difference is 50 millimeters, and we know the condition is going to be half a wavelength for that. So therefore we can put down a little equation. 0.5 wavelengths should be equal to 50 millimeters. And it's a little equation to solve. Lambda is going to equal to 50 millimeters divided by 0.5, which is going to give us 100 millimeters. So we have ascertained the wavelength of the microwaves to be 100 millimeters. Now what we've got to do next is work out what the path difference between S1Y and S2Y is if we detect a second minimum. Well, we know the conditions for the second minimum. The path difference for the second minimum is always going to be equal to 1.5 lambda. So it's going to be equal to 1.5 wavelengths. We already know what one wavelength is. One wavelength is 100 millimeters. So therefore we know that the path difference has got to be equal to 1.5 times 100 millimeters. And that comes out to be equal to 150 millimeters. So this question is a two-stepper. We have now got the path difference S1Y to S2Y to be 150 millimeters, and the answer for that has got to be response D. Question 17. A ray of monochromatic light passes through a glass block into the air as shown. There's the diagram there, and it's not drawn to scale. The critical angle for the glass block is 37 degrees for this light, and we're asked to find what angle X is. That's the angle inside the glass block. Well, we know from the critical angle we can find the refractive index, because we know from a relationship sheet that sine of the critical angle has got to equal to 1 upon the refractive index. So we rearrange that, we can find the refractive index is 1 divided by sine of the critical angle. So we can find out what the refractive index of the material is, and we put in our values. 1 divided by sine of 37, and we work that out, we get a value for the refractive index to be 1.66. So we've now got the refractive index of the material. Now our next move in our second step is to work out the Snell law to find this angle X here. But we have to be very careful, because the angle between the ray and the normal is this angle in here, which has got to be 50 degrees, because this is going to be a right angle. 40 and 50 makes 90 degrees. Now we can reverse the rays coming in here. We can come in from this direction and the rays take the same path. So we can find angle X by using our Snell's law. We can say sine theta in the air, which we know is going to be equal to 50 degrees. So sine 50 degrees in the air divided by sine of X in the material is going to equal to the refractive index 1.66. wee bit rearranging will give us that sine x degrees is going to equal to sine of 50 degrees divided by the refractive index, which we just found. And therefore we can say that sine of x degrees, if we do the calculation for that, we end up with 0.461. So all we have to do is take the inverse sine to get what angle x is, and 0.461, the inverse of that, is going to give us an angle of 27.5 degrees. We look it up into our responses and we see the angle is B, 27.5 degrees. It's another two-stepper. Find the critical angle. We know the critical angle, find the refractive index, and then do Snell's law to work our way through the glass block to find out what angle x is. Answer B. Question 18. A ray of monochromatic light in air has speed c, wavelength lambda and frequency f. The ray of light passes from air into a substance. The refractive index of the substance is 2.0 for this light, and we asked to find which row in the table shows the speeds, the wavelength and the frequency of light in the substance. Let's take a look at a diagram of what's happening. Here we have the air. This is the air up here. And we have the substance here, which is a refractive index equal to 2.0. So we can go to a relationship sheet, and we know that the refractive index n is going to equal to the speed in the first medium, which is air, divided by the speed in the second medium, which is the medium we're looking at here. So we can say the following. We say refractive index 2.0 equals v1, that's the speed of light in the air, which is c, and we're dividing that by the speed of light in the second medium. So therefore v2, if we do a rearranging, becomes equal to c divided by 2, and that's equal to 0.5 times c. So we know that the speed of light in the material is going to be half the speed of light. Look at a relationship sheet again, and we have the refractive index is equal to the wavelength of light in the first medium, which is air, divided by the second medium, which is the medium we're looking at, and therefore we do the same thing again. The refractive index is 2.0, which equals a lambda 1, which is going to be the wavelength of the light in air, divided by, I'm looking for wavelength 2. So therefore wavelength 2 is going to equal to the first wavelength divided by 2 again, which is going to equal to 0.5 wavelengths. So we can see from our knowledge here that the speed of the light in the medium is going to be half c, and the speed and the wavelength of the light in the second medium is going to be half wavelength. So that gives us these choices here: half c, half wavelength, half c and half wavelength. But the key factor here is to remember that the frequency of the light in medium 1 will be exactly the same as the frequency of light in medium 2. Frequency does not change. So looking for half the speed, half the wavelength and the same frequency, and that's going to give us answer E. Question 19, an electrical question. A circuit is set up as shown, and we asked to find the total resistance between X and Y. In this part we have to identify which is the parallel part of the circuit and which is the series part. So you can see if we have the electricity, the electric current coming along here, you know it's going to split up here. Some's going to go down there and some's going to go along there. So this part of the circuit here is going to be the parallel part, and I'll show that in a kind of yellow part. So the parallel part is where the current is forced to split, and that is an 8 ohm with a 2 ohm in parallel, and the 4 ohm is going to be the one which is going to be in series. So work out the parallel part first, and we have 1 upon RT is our equation for working out parallel resistances. It's going to be 1 upon R1 plus 1 upon R2 from the relationship sheet. So 1 upon RT is going to equal to 1 upon 8 plus the 1 upon 2. And therefore we can make that into the following. 1 upon RT is going to equal to 1/8 plus, in this case the same as saying 4/8. Or we can do it in our calculator. We're going to get 1 upon RT is 5/8. And therefore, to flip it back over again, RT is equal to 8/5. So that's going to give us a value of 1.6 ohms. So the parallel part here is going to give a resistance of 1.6 ohms. You have a 4 ohm resistor in series with it. So for the big total is going to be equal to the series part, which is 4 ohms plus the parallel part 1.6 ohms, which is going to give us a complete total resistance of 5.6 ohms, which is going to give us the response D. Question 20. In the circuit shown below, the lamps are identical. The power supply has negligible internal resistance. And we're asked to find which circuit is the greatest power dissipated in the lamp. The greatest power dissipated means the greatest energy per second lost in the lamp. Now we can go to our power equations and we can find the following in the relationship sheet. Power is equal to IV and power is equal to I squared R, and finally we've got power equals V squared upon R. Now we're not told the resistance of the lamp, but we're asked to find this greatest power dissipated. So this equation here is the one which I'm going to use because it's going to give me in terms of voltage across the lamp. So in all these circuits, I'm looking to find the greatest voltage or potential difference across the lamp, and that will give me the greatest power dissipated. Now we look at the very first circuit here. You can see that the lamp is directly in parallel with the 6 and 3 ohm resistor, but it's also in fact connected to the 6 volts. It's getting the full 6 volts here, so that's getting full 6 volts. If we look at this circuit B here, it's part of a voltage divider circuit, so it's going to only take a share of the 6 volts. So it's going to be less than 6 volts here for that one, so we'll say that the voltage across the lamp is less than 6 volts in this case. And the same with circuit C. We can see we've got a parallel part here which is going to give us a resistance, and once again the lamp is going to take a share of the 6 volts, therefore the voltage across the lamp is going to be less than 6 volts. And the same for circuit D, only the lamp is in the parallel part. This part of the circuit is going to take a share of the 6 volts, which means it's going to have a less voltage across it than 6 volts. And once again, the lamp is going to have a voltage less than 6 volts. And the same for this circuit here as well. We'll only change the value of resistance here. So the only circuit which gives us the maximum voltage across the lamp is the first circuit, because it is connected directly in parallel here, and this lamp here is connected right across the 6 volts, which means the power is going to give you the maximum power dissipated, because the maximum voltage across the lamp will be 6 volts. So the response for this question is A. The position of that ball bearer is going to give the maximum power dissipated.